my screen full screen. Thank you all. Good morning, and thanks for joining me in the morning to my talk. Just a quick disclaimer, I had a few technical difficulties, so I had to switch to an external webcam, and its cable is very short, so I'm literally sitting at the edge of my desk, so it's not my usual setup. If I look around and move around, it's just because my keyboard is on one side and my mouse is on the other side. But anyway, so interpretability and explainability are two of the hottest topics among AI researchers and among us AI practitioners. Explainable AI is often referred to as a solution to social, ethical, and regulatory considerations of using machine learning models. And in my head, when I hear XAI, I always think of it in almost two parts. One is a more technical explanation. It has a more technical lens in my head, and it focuses on how does the machine learning model actually work? How does it produce a certain outcome? And on the other hand, the socio-technical explanation is almost like, yes, the technical lens is here, and we're adding another social lens. So it's more about communicating on top of the technical information that we already have. So today, in the next 20 minutes or so, I will cover the concepts of some algorithms for interpreting the machine learning models and provide technical explanations for their outcomes. And then for the second part, I will cover how we in the Allianz Personal Data Science team, with our collaborators from the University of Bristol, extended the concept of explainability to provide socio-technical explanations. Well, before I jump to that, who are we? So Allianz Personal Lines Insurance is a general insurance firm. So we sell car, home, pet and travel insurance, and as you can imagine, as a financial services company, we're heavily regulated. And as the AZP data science team, we're a central team, and we're putting machine learning into practice, so that's our motto. We're a fairly mature team. They founded more than 7 years ago, have more than 55 members. That is a mix of data scientists, data engineers, a small group of data analysts, and data hunters. We work with different business departments. Since the inception, we've influenced more than 50 decision points. Like I said, we're a central team, and together with the support functions, we give support and we help the rest of the business, function with their machine learning and data science needs. So it can be claims, fraud, pricing, underwriting, marketing, you name it. And as a team, we focus our effort on our three team pillars that are heavily overlapping. So deliveries, these are our usual use case we work on with our business stakeholders. Technical excellence is what we ensure with everything we do, every stage of our work. And last but not the least is research and innovation pillar. So this is all about investigating what's next, experimenting and exploring what can we do differently to improve our capabilities. And we do so by working on research projects internally by leveraging the skills and resources that we have internally within the team, but also working collaboratively with our academic partners, and the biggest one being the University of Bristol. Right, okay, enough said, now back to the explainability. But let's first agree on some terminology. Interpretability versus explainability. Oftentimes these two terms are used interchangeably, but there are certain distinctions. And for the sake of this presentation, and usually I do like sticking to the explanations stated in the AWS white paper, which I actually put a reference below if you would like to go and read it afterwards. So interpretability is all about the inner mechanics of the model. So this involves interpreting the model weights to estimate the impact of individual features on the model outcome. So it's to understand exactly why and how the model is generating the predictions by observing the inner mechanics of the model. So imagine we have a simple linear regression model, And here I'm assuming x1 is a numerical feature, and by keeping everything else the same, if we increase x1 by 1 unit, it would make a beta 1 amount of change on the target variable y. So it's quite intuitive in a way from the technical sense. Explainability, on the other side, is to take a machine learning model and explain its behavior in human terms. So as Miller said, I really like his explanation. It is the answer to a why question. So why does this model predict that I would find a film boring? So more coming in the following slides on how I decide whether a film is boring or not myself. Or if we switch to an insurance context, it's why is this model telling me this car is a total loss, which basically is a total wreck in insurance lingo. And as you all know, when it comes to choosing machine learning model, there's no silver bullet. All models come with different pros and cons, and we need to make a decision. So these pros and cons, they come in terms of performance, but they also come in terms of how interpretable they are. So this takes us nicely to the concept of white box or glass box versus black box models. So glass box models or white box models are built directly for interpretability. So it means that we can understand and get direct interpretations of how individual parts of the model, as individual features, impact the final model outcome. So some of the examples of such models include, but not obviously limited to, linear models like linear regression or logistic regression, decision trees, explainable boosting machines, or automatic piecewise linear regression. So I've left a link to the papers to the last two models, and also an implementation using Interpretability package from Microsoft. So glass box models are great in terms of their interpretable nature. However, quite often they can fall short in terms of performance compared to their black box counterparts. But like I said, they're great in terms of interpretability. If we just take this toy example of how I decide if a film is boring for me or not, it is again quite intuitive and self-explanatory if you just look at, it's a massive simplification, but how I actually decide if a film would be boring and then ultimately decide whether to watch it or not myself. But like I said, it is in a way simplification. So black box models tend to be more complex, and they're oftentimes better at modeling more intricate relationships between features and the target. So they're more complex, and we cannot directly extract how the model components and inner mechanics of the model impact the outcome. So for such models, we tend to use additional tools to provide post hoc explanations, as we cannot get the direct interpretations from the model. Excuse me. So examples of those models include like the ensemble methods like random forest and XGBoost, or deep learning models. And I mentioned we need to use additional tools to create post hoc explanations. For these tools, we usually separate the model from the explanations rather from the model. So that's why they are referred to as model agnostic approaches. And we can group them into two, global and local model agnostic methods. And these methods help us extract relationships between model features and model outputs, which in turn help us create somewhat approximate explanations for the model. So the global model agnostic methods are great at creating almost a summary of the model, and I personally find them quite useful when communicating the behavior of a model, for example, at a high level with the stakeholders, for example, at the model sign-off stage. Some of the methods here include, but again, not limited to, partial dependence plots, PDPs, feature importance or feature interactions, or global surrogate models. I have included an example of a scikit-learn using a PDP is good at showing keeping all the features but one the same. How would the target change if we change the value of that feature that we're looking at? We can also use a two-way PDPs, which means that we change two features together at the same time. So good models give us a good overall look of a model. But on the other hand, local methods provide explanations for individual data points. And I find these especially useful for the models that go live, that are, for example, implemented into source system. A source system is making a call to our models. So when sending the model outcomes back to the source system, we can also send back these outputs from the local model agnostic methods, showing a breakdown of approximately how much each feature contributed to the model outcome and in which direction, whether positively or negatively. Again, some of the most common methods include ICE plots, individual conditional expectation, LIME. You might be familiar with LIME, especially being used to explain how convolutional neural networks work, and Shapley additive explanations. As a team, we have very recently open sourced a package called Model Explainer, which is a wrapper around the SHAP package, and I've left a link to our package at the end of this slide deck. So please go and show it some love, and there's good examples that can help you get started using the package as well. So here is an example for this slide. I've included an ICE plot. And wanted to show the relationship between ICE and PDP plots, which PDP is the average of all the ICE plots. So far we've looked into providing explanations pretty much only with a technical lens on, which is to an extent we are biased, as I assume you are as well. That we're data scientists. This is what we've experienced in. But one thing we've noticed that this is not enough for the cases when we have human in the loop. So if you imagine a scenario that you're building machine learning models to help decision makers. So imagine you have this setup. You have an end user who are not necessarily your stakeholders. You collaborate closely with your stakeholders, from the idea generation, scoping, to model building and sign-offs. Then you work with the support functions when it comes to integrating your models into a source system, and that is close collaboration. And maybe you have some connection and some communication with the end user, but maybe not so much. So as you can see, this end-to-end process, there are quite a lot of processes, can be quite a few different machine learning models, different actors, different systems. It's a really complex ecosystem. So the main question we have in this setup is, how can we provide explanations that are most useful to complement our machine learning models for the end user, for our model consumer, so they can make the best decisions, the most informed decisions. And spoiler alert, sending outcomes coming from those explainability tools, or if you're using glass box models of direct explanations, is not the answer. So what we realise we're missing here is a social scientist view to create true socio-technical explanations. But within the team, sadly, we didn't have any social scientists. So we turned our faces to our academic network, and specifically University of Bristol and Bristol Digital Features Institute. So BDFI is one of UOB's 5 research institutes. It's an interdisciplinary institute, and they're working to fundamentally transform digital innovation and create more inclusive, sustainable and prosperous futures for all. So we have worked and been working on a few collaborative projects, 2 completed and 2 upcoming. But today I would like to focus on Explainable AI decision-making project that was led by Dr. Marcela Gutierrez, and the PI of that project was Professor Susan Holford. So what we did in the Explaining AI decision-making project is we decentered our focus from the machine learning models and looked broader to the end-to-end process where the models are embedded in wider practice. I personally really like the way Maricela explained it. We're broadening the scope of explanations from solely machine learning models to what we call machine learning practice. And a machine learning practice, like I showed in that toy workflow slide 2 slides ago, can have multiple machine learning models, but also have different actors and processes involved. But machine learning models are definitely not the only component. So we can say we reimagined XAI by using organizational ethnography. There's also a second part of this project, which I won't be going into today, which was co-produced with BDFI and their community partners, Black Southwest Network and Knoll West Media Centre. But focusing on the organizational ethnography side, I confess that I'd never heard of that term before this project started. And in one sentence, my very non-scientific explanation of the concept is being a fly on the wall. So Maricela was embedded in our company, shadowing different teams, employees, observing various meetings. She also did interviews, so used qualitative methods to collect data, and reviewed internal documents, communications, but also the information that is publicly available about the company. So like I said, Maricela was embedded in the company, but more specifically in our team for 3 years. And I would say it worked really well for a number of reasons. So it won't be wrong to say she was at the heart of where the action is, in a way. So it's where the models are designed and implemented, stakeholder discussions are made, and this gave her a great opportunity to examine machine learning practices across the organization, starting from the idea generation, scoping together with stakeholders, and then follow the trail towards operational teams like, for example, claims and fraud, but also go all the way up towards the C-suite. And like I mentioned earlier, we're a central team, so it gave Maricela easy access in a way to connect with other business functions, and for this case, it was the claims department for us. And having a social scientist, social science researcher being part of the team also brought us very close to the project, us as a data science team and data scientists. And obviously being more on the technical side, being so close to this project also created that continuous two-way knowledge exchange for us. And we got this great opportunity to familiarize ourselves and change our mindset and get closer to more human-centric approach of designing machine learning models. So in a way, changed and shifted our thinking. Well, I can at least say my personal thinking. And I would say it won't be wrong to say that this collaboration, our academic partners really helped us bridge the gap between us AI practitioners and the AI public. It created a neutral playing field, which is very valuable. So it's almost coming from an objective academic researcher perspective and providing that outside-in view while being very, very heavily embedded in our team and in our company. So I think it is also quite important to mention here that as a result of this project, we almost changed the narrative of working collaboratively to co-creating with the business functions, our stakeholders, our model end users, our consumers, together, all together. So co-designed, co-created, better designed. And some of the impacts I want to mention is, as part of this project, we arranged workshops with claims handlers, fraud experts, like I said, different stakeholders and model consumers, and also experts from the data science team, our team. to have explainability discussions together. So it really helped to get then tangible outcome and impact from a qualitative piece of work. Sorry. And at the same time, parallel to this project, as I mentioned, we were also working to create a Python package that understanding and taking into account the requirements of our stakeholders and model consumers. So it also helped us design a better fit for purpose package. And like I said, it is open sourced on GitHub. So business end users wanted to have more conversations with us, which is great. And we were invited to go and sit with them, basically shadow their work, and watch how they interact with our models on the go, for example, when they're on the phone with our customers, and how do they make decisions with the help of our models. And it was a great, valuable experience for us. So this really opened up more opportunities for all of us to move towards more co-creative space and environment. And again, this level of increased communication led to enhanced and meaningful knowledge sharing between different teams. So now there's more information present and more learning opportunities available for the wider business on data and machine learning topics. Also, this also helped making end users, model consumers, being active contributors to explanations as well as model design. So it almost created this sense of shared responsibility. And as part of the study, one of the team members actually commented, previously we felt like we're building the models, we have to explain everything, but now it's a shared effort that everyone needs to explain their own bit, because we're not focusing on the models, we're focusing on the machine learning practices. So all in all, I would say explaining how machine learning models generate certain outputs is extremely crucial, and I hope you agree with me. And it is not only for regulatory reasons, but also for a myriad of reasons, and some of which are, first of all, sanity check, to check if the model is actually behaving as we expect it to behave for the right reasons. You might have seen that example of an image classifier model identifying different dog breeds, and in terms of identifying a dog breed husky, no, that's a dog that lives in cold conditions. Because the training data contained a lot of images with snow in the background, it turned out it was actually looking at the snow and then classifying the image as husky dog, which it can classify to a certain extent the right images, but not in a way for the right reasons. So for sanity check, it is quite important for us to understand, at least to an approximate level, what the models are doing behind these black boxes. Identifying bias, explainability, the interpretations can also be used as a debugging tool to identify bias and in turn help us mitigate that in our models. And last but not the least, social acceptance and model uptake. So demystifying what could be seen in a way as a witchcraft to model end users in an engaging way is really, really key to enable social acceptance and improve model uptake, which is what in a way came out as a result of the social science work that I've mentioned before. Right, so today we covered differences between interpretability and explainability, discussed a wide range of explanations, and before closing, I would like to add that explainability is never a finished product. It's never something that we can tick off and forget about. It is an ever evolving feature that we as data professionals need to take into account in all stages of model development and end-to-end machine learning processes. So it shouldn't be added as an afterthought. It should be part of every stage. And because only this way we can achieve co-creation and truly develop a human-centric machine learning practices. So I have added some resources for further reading, like I mentioned, a link to our Python package, a video of a presentation by myself, Maricela, and another colleague of mine, in a true collaboration sense, that we were basically explaining our different perspectives of the project and learnings. A great book I can read online, Interpretable Machine Learning book, Interpret ML package, some of the glass box models I mentioned earlier on, like explainable boosted machines. There's a package by Microsoft. And last but not the least, Miller's paper that I think you might enjoy reading and find it helpful. And before I finish, I would like to say thanks to Maricela and Kieran, because I've used some of the content and their slides, and also thank you for being here and listening. Please do connect me on LinkedIn, and now actually I will change from the full screen and look at some of the questions on the chat. So the question, what's the idea behind consensus on feature importance between different feature selection techniques like random regressive interpretation, when in essence these techniques function under different conceptual premises? Is this consensus of feature importance not contradictory in itself? It's a really interesting question. I'm actually quite keen to hear everyone else's thoughts on that, if you don't mind answering in the chat as well. Yes, I would say they're kind of different conceptual premises, and I personally don't like using just one method, especially when we're using those post hoc explanations to come up with a way to interpret the models that are not inherently interpretable. And again, it heavily depends on your problem and the assumptions that you have, even though the methods are model agnostic. It still depends on why it matters and what context you try to provide those explanations. So I personally always take everything in that sense with a pinch of salt and try to use as many different style and types of techniques as I can, and a combination of both global and local to answer that question. So I hope that kind of answers your question. But yes, they're conceptually different in a way, but all of them are approximations anyway. So I would say take all of that with a pinch of salt.